So we've heard a lot of talks about new functionality. There's no new functionality here. This is a complete retooling of existing functionality. So it's not on Stephen's word cloud of new functions. I'm going to give a brief overview about elementary functions, transcendental functions, how they're computed in high precision. I'll try and give you some examples. And I'll outline some new work to substantially speed up the evaluation of these functions. So the first thing I want to show you is a comparison. This is not by me. This is by a team that develops the MPFR package. So basically, they've taken a bunch of different packages. Don't worry too much about the timing for Mathematica here, because this is Mathematica version 6, which is from July 2007. Actually, Mathematica is comparable to the best of these systems here, MPFR. The main points I want to point out are all of these libraries use, for the basic arithmetic, this GNU multiple precision library for the core arithmetic. That's a multiplication, division, addition, subtraction. And you see that that doesn't have any support for elementary functions. So all of these other packages, all of these special purpose packages, implement their own version. And my benchmark has always been MPFR, which is by a group of INRIA, which is an extension to the GNU multiple precision library. And it's part of GCC, actually. It's used by GCC, the GNU compiler, to compute high precision approximations when actually compiling stuff. And Mathematica is actually comparable with MPFR. What I'd also like to point out, there's this new kid on the block here, ARB, this new ARB library. And the timings in bold here are the fastest system. And what you can see is this ARB library suddenly has become 4 times faster than the GNU MPFR library. So I'm going to discuss the ideas in this ARB library, and I'm going to discuss how they've been incorporated into Mathematica. Okay. So just a very quick example of the sort of thing I'm talking about. Mathematica provides 2 types of arithmetic. One is fixed precision. Here I fixed the precision at 20 digits, and I've computed the cosine of some small value. If I then go and use the inversion formula, this is equivalent to the sine function, then I get a complete loss of precision in fixed precision when the argument here is quite small. This is 10 to the minus 30. And this is a typical behavior of using a fixed number of digits. So in Mathematica, we have an alternative model called significance arithmetic, which locally models the conditioning of the function. And here what you see is you don't get a fixed number of digits, but you get a growing number of digits depending on the conditioning of the function at this argument. And when you invert this quantity to get the equivalent of the sine function, you get a completely accurate answer. Okay, so this is the kind of the default arithmetic that we use in Mathematica. In something like NDSolve, we'll switch this arithmetic off, and we'll use this fixed precision arithmetic, and we'll use local error estimation from a differential equation solver or something like that to control the error instead. So applications of arbitrary precision in Mathematica, well, they're everywhere. I mean, I've listed some, but they're really, really everywhere. I mean, they're used in all parts, even regions and stuff. Here's one example, that uses Reduce produces these solutions to x log equations, these root objects, transcendental root objects. And here I can take numerical approximations of these things and get arbitrary approximations. And that actually is computing these elementary functions to high precision. So what are arbitrary precision numbers? Well, essentially they're concatenations of integers, an arbitrary array of integers. Each of these digits in here is a machine integer. So it's an array of machine integers. And each of these block of digits represents either 9 or 19 approximately on a 32 or 64-bit machine. But basically at the heart of every arbitrary precision number is an array of integers. And that array of integers is growing and representing the number of digits that you have. And it can be arbitrarily long. So, as I said, all of the libraries that I showed on the first slide use this GNU multiple precision library. When I first started, every single library would use its own ad hoc method. Okay, this is good for us because it means if we also use this library, which we do now for at least a decade, we can compare our implementation and our algorithms to other systems, and we can see how good they are because we're all using the same core underlying fundamentals. So it kind of levels the playing field for everybody. So what I'm specifically going to talk about here is computing trig functions. So there are three components to computing a trig function. The first is a range reduction. That's to bring the argument within a range in which the approximation is going to converge. The second one is called argument reduction. Once you have it in a range where the series is going to converge, you're going to make it even smaller to try and accelerate the convergence of the series. And the third one is the actual evaluation. Now, the actual evaluation is different depending on if you're using machine precision, you might use a chordic or a minimax approximation. In arbitrary precision, we use a Taylor series. But even evaluating the Taylor series in arbitrary precision can involve different methods depending on how much precision we're using. So there's the basic summation algorithm, which is just basically going through and computing products and summing them up. There's something called rectangular splitting, which I'll outline a little bit later, and something called binary splitting, which is used for extremely high precision that's outside the scope of this talk, so I'm not going to cover that today. So the first thing to do, you have sine or x for some number or something. The first thing to do is to bring it in a range in which the series is going to converge. And you do that by subtracting off multiples of pi over 2 or of log of 2, okay, to reduce the magnitude of this argument. And here are a few different examples of different functions. And that means that we have to compute pi or log of 2 or something like that to high precision. Okay, and we have very good algorithms for doing that. Once we've done that, we have something like x is less than 1. Okay, x is less than 1. It might be 0.9 or 0.8 or something. The series is going to converge quite slowly. So what we ideally want is something quite small, okay, like 10 to the minus 10 or 10 to the minus 20, in which case the series is going to converge much, much more quickly. So then we can use functional relations to do that. And here are a couple of them. Here's one for exp. Okay, this says if I want to evaluate the exponential function at some argument, I can actually evaluate it at half of that argument, go and do that, and then just square it at the end. Okay, so I can do this like 10 times or something like that. I can reduce it by 2 10 times, so it's now 2 to the minus 10, and then I just square the result 10 times, and I get back the original input. But the actual computation that's gone on in here is much, much more efficient. And some functions are computed together, like sine is related to cos, so these two functions are computed together, and sine is related to cos. So the new idea in this ARB library, why it's so fast, is quite interesting. It uses a lookup table. Okay, so it doesn't do this functional relationship, because here, in order to make a number smaller, I had to do a squaring. I had to divide by 2, go and compute the series, and then square the result. Okay? Squaring the result, multiplication in high precision, is expensive. So what if I could reduce the argument somehow without having to pay that cost? And that's what this library does. So basically, it sets up these tables. Now, if I want to knock out, say, the first 16 bits, make something 2 to the minus 16, then I need a lookup table that's 2 to the 16 entries. That's quite a lot of storage. But I don't have to do that. I can do 2 8-bit tables, okay? And I can use a formula to concatenate those together. And 2 8-bit tables is a lot smaller than 1 16-bit table. But it still knocks out 16 bits. So here's an example to show you what's going on. This is my number, okay, my arbitrary precision number. I'm going to take the first 8 bits, okay, and I'm just going to take them away and put zeros there. And then I'm going to call whatever was in here a rational number, P1 over Q1. Okay, it's just a rational number. Then I'm going to take the next 8 bits, knock them out, just put them to 0, and I'll call whatever this purple bit here is P2 over Q2. It's another rational number, okay? Now I've got a number that's got 16 leading zeros, okay? It's 2 to the minus 16. My series approximation of that number is going to be very, very fast, okay? That's my exp of x2 here. I can compute that really quickly. But I've taken bits out here. So what I've computed here is not the same as what I had here. I have to add back in this, and I have to multiply the three things together. Okay? But this is exponential of a rational number, and I just get it from a lookup table. And this is exponential of a different rational number, and I just get that from another lookup table. Okay? So these kinds of ideas are also used in hardware, but in hardware you have restrictions with the size of the die and everything. I mean, CPUs are expensive to kind of construct. The point is here that I can build these lookup tables, and I can build them up lazily. I can just say, have two 8-bit lookup tables, fill them up as you need to. So each time I go through the exponential function, I fill out one new entry in each of these two tables. And the nice thing is for something like ND-solve, where I'm evaluating cosines or sines over and over again with very similar bit sequences in the beginning, because they're all quite near to each other, the numbers, I can just go and get all of these leading bits from these lookup tables, okay, and recycle them over and over again, instead of having to use those formulae for reducing the arguments and paying the cost of the work to bring the number down in size each time. So if I restructure the code correctly, then really there's only 4 series that I have to evaluate, okay? Arctan and arctanch, which are pretty similar except for the alternating sign, and sinch and sine, okay? Where this has a factorial in the denominator and these are just the odd numbers. Okay, so these are the only series that I have to actually worry about evaluating. So once I've got part of my result out from the lookup table, I still have to go and compute this series. Now, for the exponential functions, I can use some kind of symmetries. So here the exponential function involves all powers, but if I compute the series for sinch, which is just the odd powers, then I can use the inversion formula to get the cosinch, and I can just add the two together. So here I've only evaluated a series with half the number of terms, and just by doing a square root and a square, I've effectively got the exponential. So I've effectively cut the work in half here, because this series is like half as expensive to evaluate as this series, okay? And a similar kind of idea for the logarithm. It's a pretty neat trick. Using this identity here, we have a relationship between the logarithm and the arctangent. And here I have a series for the logarithm near 1, and I can use this series for the arctanch, which is only involving odd powers. Okay, so these are kind of tricks to kind of reduce the size and number of terms that you need to evaluate. But at the end of the day, I still need to evaluate some series. Okay, so here's a top level, just a top level implementation to show you the sort of thing you do. Basically, you take each new term, multiply it, and divide, multiply it and divide, multiply it, divide, over and over and over in a loop. Okay, and if I compare this kind of top-level implementation with what I have internally, it's more than 100 times slower. So I'll give you an indication of why that is. What's happening is I have a lot of data structures with a very, very short lifespan. Okay, I'm multiplying some product, I'm adding it in, I'm creating something for the result, then I'm throwing it away, I'm adding in something else, I'm allocating memory, throwing it away. And all of the arithmetic that I'm doing is general arithmetic for floating point numbers. It has to check for overflows, it has to normalize numbers, it has to check for changes in precision, and all of that is quite expensive. When I'm evaluating the series, I know that I'm working in a really specific range. All the numbers are smaller than 1, the exponent is bounded, nothing is ever going to overflow. So the essential idea is to just make a big memory block. One big memory block, and just put all of those numbers in this big memory block and do all of the arithmetic in one memory block and just shift pointers around doing the arithmetic. And that's why this is so much faster than actually writing it in Mathematica. Because there's no data structures, there's no overhead from repeated allocation and freeing. You're not going through these generic routines to do floating point arithmetic. You're just really working at the word level and the inside of the floating point numbers. And the second trick is that even though these are scalar divisions here, divisions are more expensive than multiplications. Okay. If I take, let's take the first 5 terms, okay, and compute the least common multiple, that's this number here, and the next 5 terms and compute the least common multiple. Then I can rewrite this, which involves all these divisions, as something like this, where these are now multiplications. And only every 5 terms do I do a division, right? So now I'm using primitives from the GNU Multiple Precision Library, these fused add multiply, which are the core of multiplication. They're all implemented, highly optimized in assembler. So I've transformed my problem into something which the library can do really fast, okay? Now the second thing that we didn't have before is another way to more efficiently evaluate the series, something called rectangular splitting. So it works like this. You build up a table of powers, okay? So I want to compute a Taylor series with 16 terms. I build up a table of powers that go up to the square root. The number of powers here is 4 powers, which is the square root of the number of terms in the series. And I rearrange my Taylor series to use these tables of powers over and over and over again, and I just multiply in a nested fashion by some power. And if you expand all this out, then you'll get like the Taylor series. If you call expand on this, you'll get the Taylor series, the first 16 terms of the Taylor series, right? But look, it's in that implementation I showed you, the basic evaluation, I had to do 1 squaring and 15 multiplications to do it. Here I've done 3 squarings and 5 multiplications. Right? So you can see that the complexity of this procedure is much, much lower than the complexity of doing it in a standard way. But there's a problem because this is exactly how the Arb library does it. It does it using this rectangular splitting, not using the basic summation. But we had something in the basic summation that's not here. And that is, when you're computing the tail end of the Taylor series, those terms at the tail end are much, much smaller than the terms at the beginning. They're higher order powers. And you can see them here. This x to the 8 is much smaller than x squared, because we're talking about something that has like all these leading zeros, okay? And in the Arb library, all of these terms are all computed to the same precision, irrespective of whether they occur at the end of the series or at the beginning of the series. So when I was preparing this talk last month, what I thought was, it would be nice if I could put what we have, this sliding precision, variable precision from the basic method, into this algorithm for rectangular splitting. And I'm pleased to say that I didn't think it was going to be possible, but I have managed to do it. It's never been done before, so this is the first for Mathematica. And it works like this. These terms that get successively clearer are computed with successively lower precision, okay? And because they're done in a memory block, that's just shifting pointers. I'm using less and less digits as I go along, okay? So there's hardly any overhead to do that, right? So I start from the end, I compute all these terms and this multiplication, and they're all done using much lower precision. Then I get to the second row, I raise the precision a little bit, compute this and add it to this, raise the precision a bit more, compute this and add it to this, and then finally do this with the full precision. So now let's look at, this is like the Olympics, and I guess it's like presidential elections. I need some sporting analogy or something like that, right, to connect with people. So this is like 100 digits is like the sprint final, okay, and this is like 10,000 meters or something like that. MPFR, which is the most commonly used multiple precision library, that's the one in blue. Mathematica 10.3 is green. It's not too bad. I mean, it gives MPFR a good run for its money, even though MPFR has this rectangular splitting algorithm, and we didn't. The fact that we use this sliding precision for an inferior algorithm, but evaluated more intelligently, we're fairly competitive. And then around this region, around 1,000 digits or so, we switch to a different method. So you can see there's a little bit of awkwardness here. This is this Arb library, okay, which is like Usain Bolt comes along, young guy, and suddenly blows away the competition here. but it's not very good at long distances, so when you get to like 1,000 digits or something, kind of fades away a little bit, and then just uses the other methods. Okay, and this is the new implementation in the development version of Mathematica. And what you can see is when I prepared this graph, I thought this is just remarkably smooth. I mean, it's one algorithm that's adapting through the precision. Okay, it's adapting itself. It's making, like in a square rectangular way, building up these tables in a nice, smooth, dynamic way. And you don't get any of the behavior that you get with any of the other systems. It's not switching between hard-coded values or switching between different algorithms. It just smoothly adjusts itself. And I always thought it was only really useful for like around 1,000, 2,000, 3,000 digits. Now we use it all the way down. I've completely thrown away the old code. This completely replaces it even at like 20 digits or something like that. And it's faster even at like 30 or 40,000 digits. So it's right from the very low end, 20 digits, all the way up to 40,000 digits. And it's the fastest of any system anywhere. This is on a logarithmic scale, so it kind of tends to compress the difference between the systems. So what I did was a performance profile too. So you can see this is how many times slower the other systems are for a bunch of different functions. And this is the Arb library, so we're kind of in the low precision range, maybe only 50% faster than a factor of 2, factor of 3. We're about a factor of 5 or 6 faster than MPFR. And in this, the MPFR algorithm for Arctan isn't very good. It doesn't use a Taylor series. It uses some kind of iterative method. And it's more than like 20 times slower in this particular range. But the important thing is that it's very fast, and it's very fast for a very wide range of precision. And that means that you can do a lot more computations, and a lot more computations in smaller precision than you could before. I mean, it's like 3 or 4 or 5 times faster is the difference between waiting a day or waiting a few hours for something to compute. And the other thing is, because of this lookup table type of mechanism, is very well suited to something like ND-solve or find root or find minimum, where you're doing very similar kinds of trig function evaluations over and over and over again. It's going to make use of these lookup tables and recycle those values. So I tried to give you an overview of the computational issues. There's been a substantial code infrastructure overhaul to try and make this. John was talking about 250 commits or something for the Git link. This is like 1,000, something like that. There's a new internal functionality. We do like range reduction, also at the word level. The new thing is to use these argument reduction cache lookup tables like the Arb library does. We use this coefficient rescaling method to reduce the number of divisions like the Arb library does. And we use rectangular splitting like the Arb library does, but in an adaptive precision fashion, which is new. It's competitive with the state of the art for low precision up to, say, 200, 250 digits. There is a little bit of interpreted overhead from using Mathematica, but used inside something like a numerical function or something like that for ND-solve or whatever, that kind of dies away. But it's the most efficient implementation anywhere in any system from around 250 to 30,000 digits. Now, it's only been like a month I've got this working, so I'm still fine-tuning like the cache table sizes and how many of them to use at what precision, that kind of stuff. And I'm still looking at bringing down this very, very low, bringing down the lower precision, 20, 30, 40, 50 digits, just to reduce a little bit of overhead there as well. So, and the other nice thing is that I've completely eliminated all of the old code. So this now completely supersedes all of the code that we've had before.